Hello, everyone. Good morning, good afternoon, and good evening. I am Jayashree Hegde, welcoming you all to this exciting webinar on unleashing the power of AI in IoT, a deep dive into HiveMQ Cloud and InfluxDB 3.0, where experts will share insights into why and how to create robust AI-powered IoT solutions. I would like to take this opportunity to welcome our speakers for today, Brian Gilmore, VP of Community and Advocacy at HiveMQ, and Jay Clifford, developer advocate for Influx Data. A very warm welcome to you, Brian and Jay. Thank you for taking time today to present this webinar. And I will let you both introduce yourselves later. And before we dive into the technical details, let me share a few housekeeping pointers. We are recording this session and we will share the recording as well as the slide presentation in a follow-up email. Throughout the presentation, if you have any questions, please drop them in the Q&A box. We will open the floor for your questions and comments after the presentation. A quick note, we have a couple of poll questions lined up for you during the webinar. Do cast your votes, your responses and feedback will help us a lot. Now let's take a quick look at the agenda. Jay, if you can just move the slide. Thank you so much. We will be exploring various aspects of data pipeline, role of HiveMQ and InfluxDB. Later, we will dive into the integration of AI and ML in data pipelines, and we will be examining real-world applications in IIoT, and finally exploring the process of building an AI-powered IoT application using HiveMQ, Quix, and InfluxDB. We also have an exciting demo lined up for you, so make sure to stay tuned for that. Now, without further ado, let's get started. Brian, the stage is yours.
Yeah, hey everybody, thanks for joining. Brian Gilmore, I lead our community and advocacy programs here at HiveMQ. I also am I'm fortunate to have worked with Jay in a past career job. We worked together at Influx Data just recently, so really good to work again together on this webinar, and I'll pass it over to Jay.
Yeah, I feel like we were the demo team. We were forever constructing new solutions and fun demos for Influx. So it's nice to be able to do it once again. But yeah, as Brian mentioned, I'm from Influx Data. I'm a developer advocate. In my past life, I considered myself a data plumber. My job was sort of connecting industrial machines on the shop floor via Kepware and InfluxDB and Grafana. So really had my hands dirty in anything OPC-UA, MQTT. That was kind of my role in sort of building data pipelines, well, very basic versions at the time. Little did I know we'd be here today talking about a more complex version.
Awesome. So yeah, I think we're just going to level set when we talk about data pipelines, exactly what we mean. I think for those of you who are familiar with the Kafka, ecosystem or other data pipeline ecosystems, you're familiar with the sort of source and sink model. And whether it's sort of just a unidirectional or one-way pathway, or as we're going to show today, a sort of bidirectional pathway. Generally, information starts somewhere. It's sort of generated like through a sensor or an application, a log or whatever, and it needs to find its way to actually get to wherever it needs to be consumed by applications or by end users or control algorithms or whatever it might be. And even more importantly, and what's really been emerging recently is when you sort of have that data in pipeline, what can you do to actually transform it? What can you do to normalize it? What can you do to, change protocols or do things in flight? And that's the sort of base of what we'll be talking about today. In this way, HiveMQ is basically the piping, right? So HiveMQ is the most trusted MQTT broker. It works on a publish subscribe model, like other MQTT brokers. And basically what it allows you to do is take information, send that information as a message to a topic that can be, ephemeral or can be persistent or can be shared amongst other consumers and producers. And so when you post that to that topic, now other devices that subscribe to that topic can actually access that data. They can process that data. They can show that data to users, or as you'll see here, they can do things like pass it off onto, time series databases and other things. So now, HiveMQ itself is an implementation of MQTT with a tremendous amount of extensions. So, we have you can check our website and you can see the information on the types of scale we support. It's very, very high in the millions of connections, pretty basically, and going much higher in sort of well-managed architectures. And that sensor data finds its way in through either direct connection with MQTT clients. We have our own client in Java and other languages as well. You can use things like the PAHO clients to get data in. And we just released a product called HiveMQ Edge, which is actually an edge gateway that does things like convert Siemens S7 protocol into MQTT and then puts it onto the MQTT topics as defined. Once that data gets into the stream, as we talked a little bit about the transformations and the extensions, you can do things like use Data Hub to run that data through policies and do policy-based transformation or policy-based routing, something I highly recommend you look at. Or you can use extensions, or you can just allow other applications to connect into the HiveMQ broker platform just using their own client frameworks or SDKs. And we have a number of databases like InfluxDB that actually plug in quite easily through their own MQTT connectors, or as you'll see here, through other connectors made available through platforms like Quix. So basically we are the plumbing that connects up all your devices to all of your IT systems, your analytics, your time series databases, all of that, and at extreme scale with great security and reliability, and a tremendous amount of usability from both the developer perspective as well as the end users in the application. So that's it for my sales pitch. I think we're going to get into some really cool technical stuff here with Jay. So we'll be back in a minute.
I loved it. HiveMQ, when I saw that release for the first time, I was like, yes, finally. That is an amazing bit of kit. So I thought that was really cool. But yeah, so I felt that one of the most interesting things to talk about when we talk about our data pipelines is, of course, the actual data itself. And you can have many different types of data go through your pipeline, but one of the key types that you'll probably deal with, especially within industrial use cases, is time series data. And I always like to level set the room on time series data because I think it's important, because it basically, if you understand exactly what we're dealing with, it offsets why we store data in a purpose-built time series database, why we use a specific solution for working with our data. So when we think about time series data, if we think about the scientific term, it's a sequence of data points typically consisting of successive measurements made from the same source over a time interval. So one of the easiest and most oldest examples to understand is stock data. So if you think about it, stock data as a single value is not interesting. We might know the exact stock value of a particular company, say Google, which is great. But if we don't know the trend at which that stock is going, why is it important to us? We don't know if the trend is going down or if it's going up. We don't know if we should be buying or selling based on if it's collapsing or if the company's doing really well and it's going up. And we can put this into a variety of verticals. And obviously today we're talking about industrial data. So think about your sensors, your PLCs on the shop floor. We want to monitor that data over a certain time period and look at the trend in what that data is doing rather than looking at a specific value in time in most cases. So we can really boil time series data into two categories, metrics and events. Metrics are predictable. They occur at the same interval. So think about us polling a vibration sensor. So taking a reading every second. We know we're going to get a new vibration reading every second, say from an accelerometer. But whereas what we cannot do with event-based data is it's unpredictable. We cannot actually derive when an event will occur. The easiest example to understand this from is, let's talk about a machine fault. Our machine might fault at some point in time, but we actually can't predict through conventional means when this machine is going to be at fault. So in this case, we can still log when that fault occurs, but we still don't know when it's going to happen, thus an event. The cool thing to know about event-based data is we can actually derive metrics from event-based data. So let's think about our machine faults once again. Now, if I say count the number of faults within a specific day, I am deriving a metric, because at the end of the day, that I will have a result every day, knowing how many machine faults I had within that day, where this machine reading could be 0 or it could be 10, depending on the number of faults. But I will always have a metric each day. So that's kind of interesting to show how we can convert this idea of event-based data into metrics-based data, something a time series database is extremely good at doing. So when we talk about a time series database, or a TSDB for short, what exactly are we talking about? And I like to sort of boil this into 4 major pillars that sort of comprise a time series database. The first, of course, is we're dealing with timestamp data. Every data point in a time series database is associated with a timestamp. And in this case, it forms part of our primary key, which means we should be able to query the data out of a time series database in timestamped order. Extremely important in that case. Another pillar that's fundamental to most time series databases is dealing with high volumes of data. So let's think about MQTT specifically. MQTT can connect thousands, if not hundreds of thousands of devices all at the same time, all writing to different topics in parallel, meaning that a time series database has to cope with this level of throughput of different sensors all writing data at the same time into one location. If we're not dealing with lots of sensors in parallel, we might be dealing with sensors that have high throughput. Think about our vibration sensor again. The average industrial vibration sensor can be anywhere from 1 kilohertz to 10 kilohertz a second. And that's and the type of data that we're dealing with there requires a solution that can deal with storing data extremely efficiently without reducing the ability to query that data. Next thing is efficient queries over time. To summarize that really quickly, think about our stock example again. We're not looking for a specific point in time. We want to bring data in over an average space of time. We want to bring a series of data points that tell us about the trend in our data. So think about time windowed queries. Think about being able to create time windowed averages, stuff like that. That's exactly what we're trying to deliver with a time series database. And of course, from the offset, just like HiveMQ, we need to be built to scale. We need to have the ability to be able to handle large quantities of data that continuously ramp as people bring more and more sensors or more plants online and pushing that through a TSDB. So one of the implementations of a time series database out there comes directly from us, which is InfluxDB. And what we're going to talk about today specifically is InfluxDB 3.0. So InfluxDB 3.0 is our new child. I say child's a bad word, but it is our brand new spick and span version of InfluxDB. And what we really wanted to leverage here was an open architecture. So an open architecture and an open data format. And this is comprised of 3 key technologies within the Apache ecosystem that we actually contribute to, and we actually use basically in sort of connection with one another. We have Data Fusion, which is our query engine. This gives us native SQL support and also a time series-based language called InfluxQL. We have Apache Arrow, which is our in-memory columnar format. This means you get near real-time queries from InfluxDB. And then, of course, we have where we actually store our data, which is in Parquet format. This gives us a highly compressed, cost-efficient way of storing vast amounts of time series data. One of the benefits of Parquet, which a lot of people leverage, is it's interoperable with loads of machine learning tasks and data science based platforms. Think about Apache Spark or Apache Iceberg. All of these integrate directly with Parquet, and we want to offer that at a fundamental level so you can interact with data at rest as well as querying data directly from InfluxDB. So it kind of gives you a little bit of an under the hood look about what we're trying to offer with the new version of InfluxDB. We're really trying to focus now on being a big ecosystem player rather than just trying to be a platform that does it all. So if we sort of take Brian's example of looking at HiveMQ and our data pipelines, how can we integrate these into one architecture? In this example, you can see HiveMQ is our backbone for connecting all of our devices together, aggregating the data into one place where we can bring this into the rest of our solution. From there, our data pipeline has the ability to fulfill two roles: the ability to ingest data, basically tap into that HiveMQ via a sink, bring that data into the data pipeline, and write that data directly to InfluxDB. But it's also got a much cooler task, and this is the one we're actually going to cover a lot in the demo today. It also has the ability to do processing and enrichment upon the data that we're storing at rest, and then write that data back to InfluxDB, where we can utilize that, say, with platforms such as Grafana, Tableau, and Superset. Now, there are loads of data pipelining solutions out there. You've got to think of things like Mage AI, which is a batch-based data pipeline, Apache Spark, Hoopla. All of these out there all have the ability to work with time series data. But there's one in particular that we wanted to showcase today, which has first-class support for HiveMQ and InfluxDB. And that is Quix. So Quix is a complete solution for building, deploying, and monitoring event streaming applications. So it actually runs Kafka under the hood, but you don't actually need to know any Kafka to be able to use Quix. Essentially, you're building your streaming application based on Python, which is what you'll see is through their platform. You can connect a series of pre-canned plugins together, like such as the MQTT sync, which can connect directly to HiveMQ to pull data into the Quix platform, and write data out to a series of exporters such as InfluxDB, where we write the data directly to InfluxDB. And you'll see through how we can use Quix to build an ML pipeline from scratch with very little effort. So with HiveMQ, Quix, Influx, Brian, what kind of problems can we solve with this architecture?
Thanks, Jay. Yeah, I mean, I think too, we're gonna, if you want to just pop on, yeah, we're gonna put a little poll or a little survey in the window. If you guys, as we move on, if you want to just answer those questions, that would be much appreciated. But we can move on. So as Jay mentioned, he's spent quite a bit of time in the industrial automation and integration space. If you can't tell by the amount of gray in my beard versus the amount of gray in his beard, I was there for a long time as well. So one of the biggest challenges about trying to manage control systems is you have so many places to look for problems, right? Sometimes it's in the physical, the mechanics of the machines. Sometimes it's in the technology, the underlying control systems, and sometimes it's in your operators, making mistakes, putting in bad set points, getting bored and messing with the formulas, all these things that human beings like to do. And so you can, of course, solve all of those different challenges in different ways. But what automation technicians, integrators are always on the lookout for is what parts of that can you actually automate? So in a situation here, we know that one of the packing machines is just having issues. We don't know, it's always down, it's always broken, it's always throwing alerts, things like that. But we don't really understand exactly why this is happening, the frequency it's happening, and how we could sort of identify the problems that are causing this breakdown. Our plant manager, who has even more gray hairs than I do, has let us know that when it's running normally, everything sort of is just, as they would say, Cadillacing, which is just running through very, very predictable and basic loops. But when it seems like right before it breaks down, it starts to break with that pattern. So the question becomes, how can we use a platform comprised of HiveMQ, Quix, and InfluxDB to automate the detection and the solution of this. And when I talked to Jay originally about this, I had high hopes because, again, I've worked with him. I know how smart he is. But I was completely blown away by like how effective the solution was and how easily it could be operationalized for anybody who has the ability to get their industrial data onto an MQTT network, pipe it through to a platform like Quix, which is absolutely easily approachable by the people on the plant floor, and then use that power of InfluxDB and the new 3.0 and Parquet and machine learning and all of that goodness to actually solve problems like this in the real world. Like this is hypothetical, but I think most of you will very quickly see how this could actually be operational. So.
Well, let's hope the demo gods are in our favor, Brian.
I know. I'm worried that I just jinxed you, but I'm sorry.
Okay. So if we look at this hypothetical problem and we wanted to have a look at a solution architecture of how we can combine HiveMQ, Quix, and InfluxDB together, this is kind of the route or the data journey, as we like to call it, sort of where our data is going. We'll refer to this solution architecture throughout the demo. The plan is we'll do a little bit of theory inside the slides, and then we'll jump to the demo. You can see it in action, and we'll swap back. But the idea here is we have our 3 robot arms all synced to our HiveMQ broker. We'll talk about that in a second. We're going to use the Quix MQTT client to ingest that data in real time, feed it to our destination sync, our InfluxDB destination sync, InfluxDB destination plugin, and then we're going to write that data to a table called machine data, which will contain our historic raw data from our machines in InfluxDB. From there, we'll use our InfluxDB sync, or also known as InfluxDB query, to query that data back out into Quix. We'll run it through an ML model, which we'll discuss a little bit later. We'll pass the results back to a destination, our InfluxDB destination plugin once again, and we'll write these results into a new table called ML results. We'll then use Grafana to overlay both the machine data, the ML results, and you can see how we can start detecting anomalies based upon this model that we're deploying. I'm not going to mention Hugging Face just yet. We'll get into that in a moment, but this is a really cool platform that we'll talk about shortly. So a little bit of theory. Let's strip back and talk quickly about data ingest. So just for the completeness sake, what I wanted to do was first talk a little bit about how I was writing the data to our HiveMQ broker. Now, in this case, what we've done is we've built a robot machine simulator. So this is basically just built in Python. And I want to take you through the sort of like the steps to success if you ever want to start using the HiveMQ with the Python client or something like a Python client for HiveMQ. So our robots go through 3 steps. They go through create machine, create HiveMQ connection, and write JSON payload topic. So each robot runs it as an independent thread, and each has its own independent connection to HiveMQ. What will happen is we have our data structure here. This is the data that's being simulated. It's a JSON style structure and contains a metadata payload, which contains a little bit of information about our source. So a machine ID, in this case, really basic, machine 1, a barcode for that robot, and then the provider that robot came from. And then lastly, we have a list of our data, our sensor readings that we have here. So in this case, we have temperature, load, power, and vibration. We're specifically going to be looking at vibration today. So that's going to be our key to detecting when there's an anomalous activity in our machines. What we're going to be doing is we're going to be writing each of the robot's payloads to a child topic underneath the parent topic machine. So each robot's ID is used as a child topic in HiveMQ. So machine 1, machine 2, and machine 3. So if we take those concepts, what does the code look like under the hood? And I just want to give a quick crash course because I think it's cool just to sort of share some learning back based on sort of my implementation. if you want to set up basically a MQTT publisher class for writing data, just a few things to note. So the first thing to note is if you want to set up an insecure connection, say to HiveMQ's public broker, which I think is an awesome like way of allowing people to start, by the way. I think that's really cool. You can use an insecure connection, which is really easy to set up. You essentially set up your MQTT client, you pass in those connection credentials, and you can preset, say, a keep alive time. Now, if we want to connect to HiveMQ, so we want to connect to the enterprise version of HiveMQ or HiveMQ Cloud, we actually need to set up authentication. This is the main method that we need to use because HiveMQ is natively secure. So we need to make sure we have a secure connection. In this case, what we have to do is we have to set up our SSL certification, and we also have to set up a username and password. And these are done within the Faro MQTT client. They're pretty easy commands just to grasp. And I believe in the cloud interface in HiveMQ, these were actually as part of the Python onboarding. So you can find those there straight away. So don't worry, you don't have to go searching for a lot of this. And so basically you set your TLS certificates, whether it's like the root machine certificates or certificates of your own, and then your username and password for HiveMQ. You also can set, just on note as well, the protocol version. This client library specifically, the Faro Python MQTT client library, is defaulted to 3.1, but I wanted to use v5, so you can define v5 as your default. And then lastly, we construct our topic and also send our data with a client.publish. So not necessarily the most important thing about the solution we're creating, but I thought it's really good to see how we're getting the data into HiveMQ from a custom way of doing it rather than just a standard MQTT publisher. So once we write our data into HiveMQ, how are we getting the data into Quix? And just a really quick run here. What we're doing is we're subscribing to all child topics under the machine parent. So we're using that hash as a wildcard there to subscribe to all 3 child topics in the MQTT broker. We're bringing that JSON payload into Quix. We subscribe to those topics. We pass that JSON payload, and then we write that to the essentially what we call the Quix stream. But really what it is a Kafka stream under the hood. But what you'll see is they elevate you away from that process. So you don't have to worry about understanding what a Kafka topic is, how that's partitioned and how that's replicated, etc. They do all that on your behalf. And if you want to play around with that level of depth, then you can. But this is kind of giving you the ability to create streaming platform without needing to know any of that domain knowledge. So let's jump into the demo and see how all of this is currently running. So I have our HiveMQ Cloud here. Brian, do you want to take us through a quick sort of overview of what we're looking at here and sort of what's offered in HiveMQ?
Sure, yeah. So anytime you hop into a cloud environment in HiveMQ, yeah, you can just hit the little plus if you want. We can see the different types. What Jay's running here is serverless, which is really, that's our most basic, like, hey, I just got to spin up a quick demo environment. It is a shared platform. It allows 100 connections, and it works on a monthly basis in terms of the size of the messages you can send. We would really recommend, though, actually, that if you're building up prototypes that you hope to scale into a production model, that you start with this new starter program. It's very, very affordable. We give you free credits to actually get started, and I'm still on my free credits. It's very hard to reach before you're actually in any kind of production scale. So, and what's nice about that is you get the dedicated platform. There's no noisy neighbor or shared resource risk. You get unlimited connections, and while you're capped on your throughput, you're looking at a megabyte per second, which is actually quite large when it comes to the text type messages that are mostly passed. So again, getting started with starter obviously is a good onboard, and then you can actually scale that up as you need to go. So just wanted to let you know that you just go to console.hivemq.cloud, or you can go to our website and click on the Get HiveMQ. We'll we'll talk a little bit about that at the very end as well. But any of the, well, either the serverless or the starter is a fair place to start if you want to try this out yourself. So,
love it. So what we're going to do is we're going to jump into our serverless version here, and we're going to quickly have a look at the web client. So if we jump over to the web client, if we generate some new credentials, so if we do a create here, you can see that we're subscribing to the machine/hash, which is wildcarding underneath. And you can see we have our 3 machines all producing our machine data here, machine 1, 2, and 3, along with our associated timestamps. So let's look at bringing this data into Quix. So this is the Quix platform. The starting view you're looking at is a visualization of the pipelines themselves. So I'm going to quickly turn on the MQTT and write raw data. So Quix is kind of broken up into sinks, transformers, and also destination-based plugins. So they're kind of color-coded that you see here. So this one is bringing data in from a source, and this one's writing out to a destination, whereas you'll see in a moment, our event detection is where we're transforming and enriching our data in some way, but it's going back onto the Kafka stream once again. So if I jump into our MQTT here, what we should start to see is we should see our MQTT data coming in. The cool thing about the Quix platform is you can see how much CPU and memory this is taking up to bring in the data. You can see round about the throughput of your data that's coming onto the Kafka stream, which I thought was a really nice concept. And you can also see the messages that are being taken from HiveMQ, like you see here. There's a ton of other features here. I'm sure you guys will have Quix on at some point for their own webinar, so I won't steal too much of their thunder on their own platform, but just to give you guys an overview here. One of the coolest features, though, is what I did was I basically used an out-of-the-box MQTT sync plugin. But if I wanted to modify that to basically transform or change the way the data is read in from HiveMQ, if I drop actually into the application, you can see that I have all of my Python code directly there, and I can actually modify all of the Python code directly. I can redeploy this. I can run this directly in here, see the changes, and then I can have a series of deployment versions so I can work out exactly how I want to bring my data in and how I want to build my data pipeline. You can see I have 2 versions here. I have production and I have HiveMQ. So I have one version I keep constantly running based on the public broker, and this one that we created together today, and created one specifically for the HiveMQ Cloud, and this is the version of the machine anomaly detection demo that we're running. So now that we've done that, we've slowly writing our data from MQTT through the Kafka topic to InfluxDB. Let's have a look at it quickly in InfluxDB. So I'm inside the InfluxDB 3.0 cloud interface. This is our data explorer here. If I scroll down to a particular bucket that we're writing our data to, which is called factory. What we can start doing is looking at our data schema. Now, we haven't covered too much of this, but what you can essentially do is define a schema based upon the JSON payload within Quix. In this case, what we've done is we've actually taken our fields, which is our sensor readings. These are the values that we want to update and iterate over time. So it's particularly vibration that you see here. If I quickly run a query here, you can see the data coming in. And then we have our metadata, which we remembered was part of the JSON payload as information about the source, is what we classify as tags. Now, tags are an interesting concept in InfluxDB because essentially it allows us to write data to a time series database that has the same timestamp, but without overwriting the other sample with that timestamp, which means in this case, we can have multiple machines all writing data at the same time and each be considered their own individual series within the time series database. And so you can see here, we have our table. We're just running a basic SQL query here to give us all tables for the last hour. It took like 100 milliseconds, just over 100 milliseconds to run that query and bring back 271 results. And you can see basically the columns here. So now that we have our data into InfluxDB, let's talk about how we can actually bring that back into Quix and enrich that data further. So if I jump back over to the slides, let's talk about the data science side of industrial IoT and where we currently are at with things. So in an ideal world, this would be every use case that we deal with on a shop floor. And I think both me and Brian agree this is not what you see on a shop floor every day. But the ideal world would be we could use basic thresholding to detect exactly when a machine fault is failing, because we know that when the machine fault occurs, the vibration is going to skyrocket and it's going to stay constant for the entire fault time. And that just means we can say if the vibration goes over, I think in this case, say 400, then we know a machine fault is occurring, send an alert to the engineer to go fix the machine. Now, in a real world scenario, this isn't the case. A lot of the time, you'll see something a little bit more like this, where we, rather than have a specific threshold that we can account for, it's more of a pattern within our analog data that you see here. So our vibration in this case, although it rises a little, it drops very suddenly, and it gives us this weird sort of jarring effect, and that gives compared to the standard data. So what can we do in these cases where we don't exactly have a structure to our data, where we can basically derive value where there's anomalies to this data? One of the answers here is actually using artificial intelligence. And the artificial intelligence we're going to use today is what we classify as an autoencoder. So an autoencoder is an artificial neural network, which essentially is unsupervised. So what do I mean by unsupervised? Well, it essentially tries to learn patterns in your data without labels or prompts from myself. So it will try and derive meaning and how to reconstruct that data based on its own learning as it goes through the different layers of the model. It originally was actually derived for video and image compression, essentially a way of basically compressing video and then bringing it out on the other side, and it would reconstruct that. Now, what we realized really quickly, or what a lot of clever data scientists found out really quickly, is it's really good for vibration anomaly detection because of how it tries to reconstruct the data on the other side. But before we get to that, here's a quick run through of kind of like the layers of what an ML model is. And we'll use a real world example to sort of showcase this. So imagine I was making my robot do a dance. And this is kind of how we're going to train the ML model to remember and recreate the dance I'm trying to get it to do. Your input layers are essentially giving the dance sequence to the ML AI itself. So we know that's kind of the dance that we want it to take. The sequence layer is basically a custom layer for a model which separates our dance into a certain beat or steps that it needs to do. Our LSTM layers are essentially our robot's memory. So specifically this encoded. Essentially what this does in an ML model is it's basically the thought or memory or brain of the ML model. It's like if you imagine, say, it learns a specific part of the routine or it learns a specific dance move, these are stored within the LSTM layers of the model. And then from there, what we do is we bring it into an encoding layer where essentially the dance moves are encoded into a simpler form. This is basically the most compressed version, which is considered the bottleneck inside the autoencoder. We then ask the robot to basically decode that compressed version and try and recreate the dance itself. And it does this through decoding LSTM layers. Essentially, what it would do is try and recall parts of the dance and try and reconstruct that back together. And as it does that, when it's reconstructing the dance, it tries to evaluate itself and see how much it erred from the original dance routine compared to the final dance routine. Now, this is really important as a concept because it allows us to use that knowledge that it's created to create anomaly detection. So how does this work with our vibration data? Well, in this case, what we're doing is we're going to train our autoencoder model on good data. This is exactly what our dance routine or our vibration data, the way our robot's meant to function, works. And it's basically going to try and recreate this every time we feed data. Now, when we run this model, if we try and run data that's considered anomalous through this model, it's going to try and recreate the data again based upon the good data that we've given it. And then it's going to find that there's a mismatch, basically an error percentage. And we call this mean squared, basically an MSE is a way of deriving basically the percentage error at which it took to reconstruct. So since it has such a significant reconstruction error compared to the good data, to the bad data, it's a great sign to know that this could potentially be anomalous data. So one of the main things when it comes to models, and one of the hardest things to basically deploy, is you could have some extremely talented data scientists that can build really clever autoencoder models, or other basically artificial intelligence or ML-based models. But the true challenge is actually bringing these into production. And this is one of my favorite meme slides to give, because it really shows the issues that a lot of people have when it comes to deploying models. The best way to describe it is, imagine if your scientists in a pharmacy created this miracle pill that could cure a certain ailment, but it has to be under the specific conditions and environment to control. What most people will ask is, how can we bring that out of the conditions and bring that into production where people can use it all the time and use this miracle pill in a production setting where we can all consume it? And this is really difficult when we deal with things like Jupyter Notebooks and Keras, which are all ML training libraries, because they basically work in a completely different way to the way most developers want to deploy ML models into, say, like a data pipeline. So what really happens is the data scientist will give some form of rogue model like this, some sort of model H5. They'll give it to their IT or their data engineers, and then they'll wait 20 years for them to work out how to deploy it. And the model will already be inadequate by this point because they would have moved on. So one of the cool things that's been actually created and is fully open source is Hugging Face. Now, if you're familiar with Git, imagine Git on steroids, but for your ML models. Hugging Face is a way of basically uploading, storing, and evaluating your models, and also a way of deploying these models directly via a consumable AI to your data pipelines. And one of the coolest things here is Quix is integrated as a native plugin directly with Hugging Face. So you can bring your models that are uploaded by your data scientists in, and you can bring them in for incremental testing and production deployment. And that's exactly what we're going to do with our autoencoder model that we've trained. So just a quick look at the architecture again. The last bit of the demo that I'm going to show you is essentially us bringing the data back into Quix. We're going to bring it through our query engine. We're going to go through our ML model. That's our autoencoder that we've discussed. We're going to write that data to our ML results. And then finally, we're going to visualize that directly. So if I swap back over to our demo here, if I jump into our control panel, what I'll start to do is create an anomaly in our data by selecting that on machine 1. If I quickly jump into our Quix pipeline, you can see this event detection. And if we have a look at the logs, essentially what we're doing is we're bringing that vibration data back in through our InfluxDB query. So we're basically bringing the last 2 or 3 minutes worth of data in every 30 seconds. And what we're doing is we're creating a new column called is anomalous. And this is basically the autoencoder attempting to derive whether the machine data that it's seen is anomalous, or if it's considered, if it's anomalous or if it's not. And then we also have the MSE percentage, which is basically that result that we derive to see how sure the model is that there was an encoding error that could be considered an anomaly on that data. If we look at that in our data explorer, we write that in as an ML results table. We run that query, and you can see that we have our MSE percentage We also have a stream ID, which is our Kafka stream ID, just for completeness, along with our vibration value and whether we consider it anomalous or not. So what does this look like as a Grafana visualization, and how can we overlay that on top? So if I update this to 10 seconds, refresh, we refresh this just now. What you can start to see is, if we sort of evaluate over time, is when we start to have anomalous data, we start to actually pinpoint with the autoencoder the ability to flag when this data is becoming anomalous. If I bring this down to 10 seconds once again, and we put this back on to 5 minutes, like so, what we'll start to see if I turn the anomalous data off is we'll start to evaluate to see that we'll have basically a lot less anomalies being detected by the robot. Sorry, detected by the model. Now, what you'll see is in normal based data as well, we will see what we call false positives. This is something that you should talk to your friendly data scientists about. We've really sort of given you a basic version of the autoencoder in terms of how we developed it. But essentially through fine tuning, you get much better results. And there's definitely ways that you can, that's one of the main reasons why you have data scientists on your team, to be able to basically tune and work with these models to create better results. And so what you can see here is we have all our anomalies and our good data coming back in, which is considered non-anomalous. So I hope that gives kind of a good picture of what we're trying to aim to do with our sort of our AI ML pipeline. I think I've waffled on enough, so I will give it back to you, Brian, if you want to sort of bring us home with a summary and conclusion.
Good God. No, that was amazing again. And I think now, even hearing you walk through it in depth, it's like, this is actually achievable and operational. Like, this is huge. I think the cost to do this, as compared to like signing up for some big data science machine learning solution that's going to run on your industrial data, like, I mean, this is probably in the dollars to do it at a reasonable scale. So very, very cool stuff. You can move on to the next slide. Yeah. So I feel like this is obvious, right? Like we have the ability now, using platforms like HiveMQ and InfluxDB 3.0 and Quix, as well as like Hugging Face and other tools for doing ML ops, to actually operationalize anomaly detection and real anomaly detection using autoencoders right there in the platform, right in front of you. You don't have to work with your IT teams to get at this. You can start to do it online or offline, whatever you need. And it is scalable, right? Like, this could scale from 1 machine to 100 machines to 1,000 machines to more. And that's a really exciting prospect, I think, for a lot of people who are struggling with these types of solutions already on the plant floor, whether they're waiting for a consultant to deliver something after 5 or 6 years for multi-millions of dollars, or if they have signed up for, any of the sort of come and you go, let's say, artificial intelligence solutions for the plant floor that have come out over the last decade. So you can move on to the next one, Jay. I don't mean to, but yeah. So what do we do from here? I think this is like the super exciting part, is like, the more I work with Jay and the more I work with InfluxDB, like, the more my mind just moves to like, oh my God, like, what's next? So like, think about what we just saw, right? Imagine putting another autoencoder or some other clustering or labeling algorithm into the pipeline there, so that you could take those anomalies and actually classify them as what they are. It's a shaky motor, or it's a broken belt, or it's bad bearings, or whatever. And then you could have a time series of that, and you could be passing that back onto the MQTT network, so that operators could be seeing in real time, not, a lot of up and down lines, but actually like what the current state and condition of the machines are. I think another thing too is that like, everybody's super excited about LLMs right now. I am too. ChatGPT is changing the world. Think about, like, as they get better and they get faster, all the things that GPTs will be able to do, or LLMs will be able to do in this model as well. Automatic protocol translation, automatic interpretation, conversion of machine language into human readable language, all of that. Speaking of human readable language, why are we going to dashboards still, right? Like, I don't mean to be like the pushy futurist, but couldn't you just like hit the button on your phone and say, hey, Jay, tell me about how many alerts and how many anomalies and how many failures I have in the plant I'm in right now, and integrate it with your geolocation and all of your machine data and your historical data, and provide those types of insights on like on demand. It's just huge. It'll be great. And then, of course, let's not forget that a lot of old guys like me are starting to retire from the plant floor, and they're taking with them all of the nifty little tricks to keep the machines going, right? And when they leave without adequate turnover, it could be very difficult to take all of that encoded sort of tribal knowledge in their brains and translate it over to the new digital native young operators who are joining the staff. And that's both a cultural problem as well as an actual technical problem. Like, how do you pass on 50 years of experience? And what gets really cool there is you could actually start to use tools like MQTT and InfluxDB and Quix and machine learning to actually see how these people are addressing problems. How are they troubleshooting? How are they fixing things like that? And then you can encode those, and then you can follow up on, when a new technician is trying to adjust a problem or troubleshoot something, are they following that path, or are they an anomaly? And if they are an anomaly, what can you send them immediately to actually solve the problem? Like, is it documentation or a standard operating procedure? I don't know. Once we get there, suddenly we can have assistants that are helping people actually do the job. So now there's a lower barrier to entry in terms of technical people on the plant floor. There's also a lower error rate, higher safety, all of that. And then we get into all kinds of crazy things like artificial intelligence created dynamic user interfaces, which are specific on like user personas and properties. And then finally, what I think is the holy grail for all of us everywhere are self-defined digital twins, where the machines are actually making the connections between the sensors and the machines and the applications and the, everything that's in your sort of ISA95 tree. It's automatically creating those trees and creating multiple trees. So you can look at things operationally, you can look at them physically, you can come up with all kinds of different things. And getting AI and IoT integrated in this way through platforms like, HiveMQ, Quix, InfluxDB is the door to all of these use cases. So I would challenge you guys to start playing with this stuff, figure it out, share it with the community. And I think like everything's going to change if y'all do that. So appreciate the time there.
I mean, I agree. Like, I feel like if I could have walked onto a shop floor and asked the machine how it was doing that day, it would have made my life 10 times easier. I would have been out of a job as a data plumber, but still, I think it would have been a great prospect. I could just been a machine doctor instead. I think that would have been pretty cool. So I am a huge practitioner, like Brian is, on, we've done a lot of talking and a lot of demo showing, but really the proof is in the pudding. We have provided the entire demo as a Git repo, so you can follow this QR code. I think we'll send the slides out at the end, and or the recordings. You can pause here. And basically deploy the demo yourself, quickly launch a HiveMQ free cluster, Quix as well, and InfluxDB on a free tier, and just set up the demo and basically start to work out how you can integrate your own domain knowledge or your own ML models that you're trying to create yourself into the pipeline as it currently stands, and sort of speed up that development process for yourself. So definitely check that out. If you have any problems whatsoever in setting this up or have any questions, this leads me greatly onto my next slide. Come join our InfluxDB community. We have a vibrant, active community in InfluxDB on Slack and also Discourse. I hang out mostly on Slack, so DM me there or drop me a message in the thread. Come talk to me there about what you're trying to do, and I'm more than happy to spend the time to work out how we can sort of even collab and do something together. So that'd be my spiel about the community. I would not be a DevRel if I didn't.
Yeah, likewise, if you want to just hop on to the next one, because I know we're running out of time. I'm going to grab some minutes for questions, but same thing here. We've got a Slack channel as well. You could just grab that QR code either now or through the slide download or watching the recording. Join the community and let's start talking about this stuff. Like, I think AI and IoT as an integration is where the conversation should be happening right now. Along those lines, we've got an event. If you are in EMEA, we've got an event called Connect. This is sort of our MQTT enthusiasts and community group. It's a brand new group. It's happening in Munich on December 7th, but you can grab that barcode as well. All of our stuff here is available, like our downloads of our community edition, our open source editions, our Docker, and of course console.hivemq.com, which is where you can go to spin up your free or your starter plan. Check out university.hivemq.com too, because we have lots and lots of free courses there for you to learn about HiveMQ, to learn about MQTT generally, and we'll be doing a lot more in terms of IoT generally, AI generally, etc. So that's that. And move on to the next one, which I think is questions, right?
Awesome. Thanks so much, Brian and Jake. This was really amazing. And thanks to all the attendees who have been giving us reactions and thumbs up. And it's really encouraging. And thank you so much. So let's open the floor for questions. Before we start the Q&A, I would like to launch a second poll. I will keep it open till the end of the session. I request all the attendees to cast your votes. Thank you so much. Just give me a minute while I launch the poll. Yep, it's up. And we will be able to cover a couple of questions because we are close again really fast. I'm actually looking at the Q&A box. I think one of the questions is for you, Jay. Andrew was asking, is there a plan to release a community version of InfluxDB 3 on Windows?
Quick answer is yes. We're hard at work at the moment creating our community OSS version of InfluxDB 3.0. So stay tuned for next year. We'll have more information on that.
Awesome. And Carl is asking, will sample code be available on GitHub? I guess you already shared the GitHub. Carl, you have the answer. Yep. So so Jay and Brian's contact details will be provided via the slides that we will share via the follow-up email. So you'll be able to contact them after the session is over as well. Awesome. Cool. I'm looking at the Q&A box again. Sahil is asking my question clarification on handling offline scenarios for MQTT clients utilizing persistent sessions. Could you provide insights into managing client disconnections in MQTT with persistent sessions? Additionally, I did like to understand strategies for scaling the setup effectively.
So yeah, I could literally talk about this for another hour, but just to give you the quick the details, the clean session flag and all of that, or you can use session expiry, I think on 5, is what you want to set to make sure that those are persistent sessions. I think the other thing that you want to look at sort of on, the source side, whether it's a client or whether or not it's just another broker that you're using sort of as a bridge to forward messages, you want to make sure that the queuing is set there to sort of, save and retain the actual messages for long enough. I think a really good way to do this is to use HiveMQ Edge, because it has a lot of that it's built in, it's very easy to implement, but you can also find that documentation on docs.hivemq. Quality of service is also very important. You want to make sure that you're using 2 or 1 or whatever, to make sure that message gets delivered when the broker does reconnect or the client does reconnect to the broker. And then for scaling, clustering and load balancing is exactly what you need to look into. And that's a place where we have really done a tremendous amount of extension on top of the core of HiveMQ, on the core of MQTT. And it's why MQTT. And it's why we would recommend that you take a look at our enterprise and our cloud editions when you need to scale to very large production scales. We have customers who are doing millions of devices, right? And tens of millions or hundreds of millions of events or messages per second, which, that's a lot. That's a big scale. It's I think it's more than Twitter, which is kind of ridiculous, but this is just their own private MQTT network. So just definitely take a look at the docs, and we can post or we can send it as part of the email as well, Jayashree. I'll send you the link specifically to where to look for this.
Awesome. Thanks, Brian. I think we can take up one last question before we close the session. So Sean is asking, and he also has a feedback, great presentation. Definitely, thank you so much for that feedback. And the question is, does Quix and InfluxDB play well with already established historians with tons of time series data? Also, for a small manufacturer with distributed PLC data installation, would you even recommend going with a historian or a OPC UA?
Well, I'll answer that quickly, and I'm going to hedge. I apologize because this is a very public forum. I will say personally, if I was on the plant floor right now, I would be looking for PLCs when it comes to new projects that speak MQTT natively, right? So they're already out there. If you take a look at like Opto22 and some other companies, I think Rockwell has one that's MQTT native now too. So the answer is no on the OPC UA. But if you do only have OPC UA as an option, there are great gateways between OPC UA and MQTT. Like check out, say for example, HiveMQ Edge, I believe has something there that would help out. There's also stuff from Kepware and things like that. In terms of integrating data from the historians themselves, I think the sort of connectors for databases, like if your historian supports a like a SQL interface or something like that, you can run those queries, you can parse those queries, you can put that data out on the broker either as a flat file. Because remember, MQTT doesn't only send single message data. You can encode stuff as binary and move it around, do all kinds of cool things with it. So yeah, again, I think it's like we have to acknowledge the fact that like we're not building every new plant floor from like today on. So like there will always be integration challenges. I guess my guidance would be get it to MQTT as quickly and as early as possible so that you can take full advantage of the entire ecosystem of really advanced technology that's popping up around MQTT. Like you just don't see this kind of activity and energy around OPC UA for whatever reason.
And I just think, just to literally jump on that as well, is when it comes to InfluxDB in this situation, especially if you've already got historians in place, I think like we're a great bolt-on feature. I mean, one data integrator put it to me is like, you're a great gateway to the shop floor for your data scientists and your data engineers without disrupting the current flow of your factory, that we've hardened historians that have been there since the dawn of time. The idea here is you can pull off all of this infinite raw data from your machines without causing compromise to your current systems that are running on the shop floor. So, you know, even if you're starting fresh, then yeah, you can integrate InfluxDB as your own version of a data historian with MQTT and everything else that we've discussed today. But if you've got something that's running and running well, then think about it as a bolt-on solution to help enable you get to some of these sort of ML and AI solutions.
Yeah, awesome. Thank you so much. So we are really at the top of the hour. We'll have to end the session today and call it a day. So thanks, everyone. Thanks, Brian and Jay, again for an awesome presentation. Thanks to all the attendees who joined us today. And stay tuned with us until we prepare the follow-up emails for you guys. We'll get the recording up and we will share the slides as well. So yeah, so thank you so much, everyone. Thanks for all those reactions. And see you all next time.
Thanks, guys. Thanks for hosting.
Thank you.
Bye-bye.